Hello students, in this session we are going to learn the fundamental theorem of linear dependence. If n vectors spans a vector space V containing R linear independence vectors, then n is greater than or equal to R. That means if the vector space V contains n number of spanning vectors and R number of linear independent vectors, then always n is greater than or equal to R. Proof is like this. Let V be a vector space over the field F. We are considering V of F as the vector space over the field F. Let A equals to it contains n number of vectors alpha 1, alpha 2 up to alpha n which spans V. Which spans V means what? Every element of V is a linear combination of elements of A. That is, L of A is equal to V. A spans V means L of A is equal to V. Let us take another set B. It contains beta 1, beta 2 up to beta R number of vectors which are linearly independent in V. The set B is linearly independent set in V. We know that any vector belongs to the V set vector space V. Any vector beta 1 belongs to the vector space V. It can be expressed as the linear combination of n number of alphas. That means A1 alpha 1 plus A2 alpha 2 up to An alpha n, because the set A spans V. Any vector belongs to V, it can be expressed as the linear combination of the set of vectors in the set A. Take beta 1 to the right hand side. So, beta 1 coefficient is minus 1. Since minus 1 is non-zero, the coefficient of beta 1 is non-zero means there exists a scalar, at least a single scalar exists. That means what? This beta 1 can be included in the linear dependent set. Beta 1, alpha 2 up to alpha n is linearly dependent set. In earlier theorem, we studied that if there exists a linear dependent set, if we take any vector from linear dependent set, it can be expressed as the linear combination of its preceding vectors. So, beta 1 A alpha 1 beta 1 alpha 1 alpha 2 alpha n is linearly dependent set. So, there exists some vector alpha k other than first vector which is a linear combination of its preceding vectors. So, delete the vector alpha k because we are having n number of vectors spans V, no. So, here beta 1 is included to the set. So, we are going to remove some vector which can be expressed as the linear combination of its preceding vectors. So, we are taking the alpha k vector. By deleting that alpha k vector, by deleting the vector alpha k, the resultant set will be A1 equals to beta 1 alpha 2 alpha k minus 1 alpha k plus 1. That means the vector preceding to alpha k and forwarding to alpha k exist, but not alpha k minus 1 comma alpha k plus 1 up to alpha n. Here we have removed alpha k means it has only n number of vectors. Again here considering another element from the vector space V beta 2, again it is the linear combination of n number of vectors from the set A1. That means in A1 we have the elements as beta 1 alpha 2 alpha k minus 1 alpha k plus 1 alpha n. So, using these vectors we have written one linear combination. So, beta 2 by taking to the right hand side, its coefficient will become minus 1. Again, since it is minus 1, it is non-zero. This beta 2 can be included in the set linear dependent set. Again, from this set we name this we can take one vector from this set which can be deleted, because here we should have n number of vectors. Beta 2 included means it becomes n plus 1 vectors. So we are selecting alpha j, which is greater than k. After alpha k, we are selecting alpha j, which is the linear combination of its preceding vectors. So delete that vector alpha j. The resultant set will be A2 equals to beta 2, beta 1, alpha 2, alpha k minus 1, alpha k plus 1. We have deleted alpha j. So alpha j minus 1, alpha j plus 1 up to n, alpha n. Here also we are having n number of vectors and which still spans V. By proceeding this way till all betas are exhausted, we get the resultant set will be AR equals to beta r minus 1, beta 2, beta 1. So R number of betas here together with some alphas will be there, which together forms the n number of vectors, that means which contains n number of vectors which still spans V. Therefore R number of betas plus some alphas together form n number of vectors. That means what? Always n is greater than or equal to R. R together with some alphas forms the n. So n must be always greater than or equal to R. That is, number of spanning vectors in a vector space is always greater than or equal to number of linear dependent vectors in a vector space. Okay. Thank you.